Welcome to our small talk around big data, and we are very pleased to have Dr. Ouyang, who is a Stevens alumni, here from a member of the technical staff at Verizon Wireless, here to talk about big data and its implications for 4G networks. So with that, Yi.
Thanks, Chris. Good evening, everyone. And it's very happy to be here again as a Stevens alumni. Very glad to see the BIA program is now being well organized by Chris and Professor Stoll so well. And actually, I'm actually very jealous of everyone in the room in here. When I stayed in Stevens many years ago, there wasn't a BIA program yet. So any students wanted to study data science and engineering, he had to choose courses from 3 different departments, like from engineering, electrical engineering, from computer science, and from mathematics department. But since now we have BIA already, we have a very good opportunity to receive the very professional and very academic trainings to strengthen your expertise and skill set in data science and engineering. And actually, I have seen most of our graduate students have been very ready for the job market. I interviewed one of our graduate students last month, and finally he got a data scientist offer from my company, which is Verizon Wireless headquarters. So very happy to see the rapid progress in BIA. That's coming back to the speech for today. The title of the presentation is to leverage big data for LTE. From the title, you will be able to foresee that this topic is a disciplinary research between big data and wireless communications. So I assume the audience in this room will be either coming from BIA program or coming from electrical engineering department. Let's move forward. First, it's a little bit about myself. I obtained my PhD and a master degree from Stevens and Tufts University, respectively. I'm now working in Verizon Wireless headquarters, performing research in big data and also in wireless communications. Basically, I'm leveraging the big data statistical model, machine learning, and data mining approaches, applied them to the wireless communications. So let's start from big data along with networks. Let's see what will happen in every minute in our wireless networks. Give you some data. In each 60 seconds, how many data and messages are transmitting in our wireless networks and in the internet? For example, for Google, there are more than 700,000 search queries by Google. Then there are more than almost 400,000 Skype minutes happening in each minute. There are also more than 90,000 tweets posted by Twitter every minute. And the heaviest load generated by YouTube, there are more than 600 new videos posted by YouTube every minute. It counts more than 25 plus hours in total duration per minute. Another 2 important number for you to remember is 2.5 quintillion bytes of data are newly created every day. And another number is 90% of the data in the world today has been created in the most recent 2 years. That means actually a rough number is every 2 years our data is increasing by 9 times in every 2 years. To me, it's more like a super exponential increase. But what does that mean to our wireless operators? Such huge amount of data generated every day every minute and every second brings heavy and much burden to our wireless networks. So we have the responsibility to carry out and to roll out the most state-of-art mobile internet networks over the country. For example, these pictures displays the most 4G LTE coverage throughout the country for Verizon Wireless. And we see the red colored covered area is supported by 4G LTE already. I would say it's more than 60% in the country have been covered by LTE already. And also, another important numbers for us to find is there have been more than 500 markets with 4G LTE coverage. More than 60% of the overall mobile data is now being carried by LTE already. So most of our, obviously the top 4, the tier 1 mobile operators throughout the country have carried out the very good backbone and infrastructure to support such a huge amount of data to be carried every day throughout our networks. On the other hand, from our mobile operators' perspective, we are able to collect so much data every day. But how do we mine them? How do we make use of them? From an aspect of the mobile operator's perspective, we summarized the 4 aspects that we can leverage big data for. In particular, as a wireless network operator, we want to leverage our mobile wireless data to study the network performance and to forecast our future network traffic. On the other hand, we want to leverage the measured and testing data from our testing warehouse to study the smartphone device quality. And also, we carried over many applications and services on the network, which is on the level 7 of TCP/IP network structure. We also leverage such a big data to study the performance of the applications and the services running on the network. So today, I want to have 3 brief case studies to display how do we leverage the big data algorithms and models to study the wireless networks. First of them is to do the network traffic prediction analysis. The second is to study the network performance. And the last one is a very interesting case study to evaluate the device quality using big data. First, network traffic predictive analysis. Traditionally, I know every students in here, if they studied the basic statistics background knowledge, they must have known the time series, which is one of the very popular formulas and algorithms for us to train anything. The most, I would say, the very popular time series algorithm and formula is, for example, moving average, weighted moving average, exponential smoothing, and so on. And I would say these techniques have been widely used, accepted, and been very popular among people to train anything in your work. Of course, it's not an exception. We also used to leverage this formula and this technique to forecast our network traffic. But the disadvantage of these popular methods are also very obvious. For example, the simple time series, no matter it's exponential smoothing or moving average method, it's just simply relying on a few previous measured points to forecast the future, and it's not very sensitive to the spikes, to the outliers in your measurement data samples. And one of the most important drawback of the traditional time series is it is less accurate in trend the gradient of the slope in each interval. So we make a new approach here. We call it traffic decomposition. We decompose each measurement point into 4 different pieces according to the traffic nature in our wireless networks. For example, we decompose any given measured point into 4 points or 4 sub-factors in here. The first, we call it a trend factor. Trend factor is more like how the user behaviors, how the rate plan policy and the change of user numbers are impacting the LTE network traffic in a long period. Such a long period, based on our domain knowledge in wireless network performance study, is 30 to 90 days, meaning we are looking at the dynamic changes or the generic trend over the next 30 or over the previous 30 to 90 days. Such a pattern happening in the previous 30 to 90 days, we organize it as a trend factor. And the second sub-factor in here we claim is the seasonality factor. What is the seasonality factor? We know the meaning of seasonality, but basically, according to the traffic pattern and the user behavior every day, every week, and every month, we claim the seasonality is like a periodical change over a certain period, which counts 7 days. I will display a seasonality factor in the next few pictures for you to understand what is the seasonality factor. Burst is even easier to understand. Burst is, obviously, is more like ad hoc, unexpected, or known changes, which is very different from the generic trend and the seasonality factor. For example, the burst, we claim many bursts every month and every year caused by some, for example, some gambling day, festivals like a Black Friday, and also, for example, a game day Super Bowl game, right? We claim such event-based or non-event-based spikes as a burst. And what is the random error? It's the easiest to understand. 1 minus trend minus seasonality and minus burst equal to random error. So we decompose each measurement points into 4 different sub-pieces, and to trend these different 4 pieces respectively, and then combine them together at the very last step. This is a sample picture that we decompose our traffic, actually. The first row is the very original measured data, and then we decompose it to seasonality, trend. Here is a remainder. I have to decompose it again to extract the random error from the burst in here. I claimed another advantage that our new approach can overcome is in the traditional time series, if some intervals, some small time series in each interval stays, the slope of these intervals stays very flat or even very gradually decreasing step by step, in your future forecasting intervals, your forecasted time series will be going down and down and down and down, which is wrong at all. Because, for example, if we just follow the traditional time series, exponential smoothing, we go through such a few intervals which are represented by the measured values in each small interval, then our forecasted value will be going down and down and down at last to 0. That means in a future, in a certain time, my forecasted traffic will be going to 0, which is incorrect at all, right? This can be represented by a very typical example. For example, in a school area, in each May, June, July, and August, most of the students go back home. There hasn't been many traffic, right, in such a 3 months every year. If we just follow the simple time series, we have the measured value in May, June, and July. But if we just, after we simply apply the traditional time series, we will find in August 9, in September and October, the traffic will be going down until 0. So that is, on the other hand, that is the advantage of our new approach. Our new approach can detect the trend in each interval so that we are able to compensate such decreasing trend originally. So in this case, we will overcome such an error. Then we will move it back, and it's slowly and slightly increasing in the future. That is a very typical example. I call it a school example, and to display the advantage of our new approach. And then in here, we are able to detect the seasonality. You see, this is the measured value from Monday to Sunday in here. You see, if we identify the seasonality of our time series as 7 days per week, you are able to find at least from 1 to day 5, which is from Monday to Friday, right? All the measured points are very similar each day, right? And on Saturday and Monday, it may be slightly different. But anyway, it's very useful for us to identify a seasonality by identifying the seasonality period to be 7 days per week. So in this case, I would say seasonality rather than the trend factor is more like a small period, 7 days rather than 30 to 90 days to identify the traffic pattern and user behaviors. Then at last is the burst, as I said just now. Burst normally is caused by what? Caused by those significant changes from the traditional trend and seasonality factor. It may be caused by gambling day, festivals, and a game day. So how are we able to identify those spikes from day to day, from month to month? We do this. We have to identify if this point is a burst or not, right? Normally, the traffic data every day, every minute, and every second do not present like a normal distribution. If any people study electrical engineering, he will know the traffic pattern behaves more like a Poisson distribution rather than normal distribution. Let's consider the best scenario. If your measured data training group, your training set presents like a normal distribution. Okay, it's very easy. Let's just set up minus and positive 3 sigma as a threshold for us to identify if a point behaves like an outlier or not. If it's not behaving like a normal distribution, simple method for us to apply, we call it IQR, interquartile range. Just Google and Wikipedia it, you will find the very simple formula for us to identify the threshold based on the IQR formula in here. Okay, so once we apply either normal distribution or IQR method to identify if any measurement points is a burst or not. Okay, let's see if we identify those points are bursts. What are we going to do in the next step? We are going to do a cluster analysis. We want to label these points as their nature. For example, we want to label all the outliers or the spikes by the time, what time it is happening, every night, evening, or morning, the geographical location, is it in the shopping mall, in the highway, or in a school? And also the event labels. For example, if I know really the November 27 is Black Friday, okay, I will absolutely label these sample spikes as the Black Friday spikes in here, bursts in here. Then at last, after we clustered all the measurement bursts points, we are able to generate a burst table for each cell tower throughout the country. So in this case, we are able to identify the burst points for each cell tower in this country. So that is the last step. We identify the third sub-factor in the traffic measurement point. You see, at last, you may see our validation results. This is the validation result in our training group. The red curve represents the measured value, which is the true value, and the blue points, the blue curves represents our fitted value by our new approach. You are able to see these two lines are overlapped very much with each other, right? So it's majorly a rule of thumb to let you know our accuracy rate can reach more than 90% between the training group, between the true data and our measured data in the training data set. However, you are able to find, for example, in this figure, there is a large delta between the red and the blue curve in some spikes, right? In some burst point in here. You see, this is a very high, this is a burst point with very high value in here. This is also caused by the inaccuracy between our measured value and the true value in the burst sub factor in there, because we, for this particular point causing very large error in here, that means we didn't have a chance to identify very accurate burst set for the particular cell tower in there. So we need to improve the burst set in here for those particular points. So just now, I just actually had a very quick review because I have 3 studies to go through. So the very first case study was going through very quickly. I will slow down a little bit from now on. If you have any questions, feel free to interrupt me at any time, okay? This case is more interesting, but requires you to have a little bit background knowledge in wireless networks. But I will use the layman language to explain it very easily and nicely to you. Okay, wireless performance evaluation. From the aspect of our wireless operators, we want to have our networks to have very good service quality, very good voice quality, right? But is there a way that for us to evaluate its performance? Yes, of course we have. But we need a model to validate it, right? So a very typical performance indicators in any wireless networks, we call it call success rate, meaning how many calls you make are successful or failed, right? This is one of the most important KPI in our wireless networks for us to evaluate if the quality of the network is good or not. So in our case, I will use call success rate, or you call it call retention rate, to evaluate the network performance. But anyway, this is just one of the typical performance indicator to represent network quality. For our case, I use this performance indicator to represent the network performance for now. Okay, so what we are going to do is we want to investigate a relationship between a 4G network KPI, which is call success rate, and its network resource. What is the network resource? Let's use a computer as an example. If you want your computer to run very fast, very quickly, what computer resource you want to have? You want to have very good CPU, right? This is one of the PC resource. You want to have very good, strong memory. This is another PC resource. Also hard drive, right? Blah, blah. Those items, we call it PC resources. Similarly, if we want our network have very good top level of performance, we want our network resource to be very sufficient to support a very good performance in the network, right? So in the network, we are able to investigate the relationship between its performance and the network resource. So in our example, I've used the channel usage, the wireless channel usage. If you don't understand what is it, just simply think it is a memory or hard drive in PC computer, okay? Then I'm going to quantify and validate the relationship between the network resource and the network performance. Okay, very simple example right now. Let's say in Verizon wireless networks, we only have one people in the country's network. We only have one people. What does that mean? It means these people only consume the very limited resource in this network. You agree? Right? No problem, right? If you have problem, stop me, because this is a little bit hard to understand if without the domain knowledge. And then, okay, now we have one people inside this network. These people only consume very little, limited network resource in this network. So what you can claim is, I'm able to foresee the call success rate will be very high, right? Because I only have one people. I may just call it outside the network to an AT&T user. Then, okay, we have one people already. Then you add another people. Now you have another people. What will you foresee? You maybe foresee, okay, I just have two people only. My call success rate in this network should be also okay, should be also very good, right? It may be slightly decreased, but generally it should be also very good. Then you add the third people, the fourth people, the fifth people. Once the people user accumulation gets a particular point, let's say you have almost thousands of people in this cell tower. Okay, a situation may be very likely to happen is this cell tower, the network in this cell tower may be crashed because of too many people at a particular point. Right now, we claim this point as a cliff jumping spot. So at this point, your network is crashed, you jumped the cliff. Okay, so up to now, okay, we have no mathematical formula to validate this relationship. But we foresee such a relationship between a call performance and the network performance in terms of call success rate and the network resource here is not a linear relationship, right? So this light blue curve is not correct. We foresee it may be like this S curve, but we need mathematics to approve this relationship. Okay, then what we are going to do is to leverage the second order differential equation to prove this relationship. We assume what? We make a very first assumption. The change of LTE network performance indicators to its network resource. This is a y-axis in that figure. This is x-axis in that figure, right? The partial differential of these two components, the change of KPI, call success rate, to the network resource is represented by what? It is represented by the current level of the KPI. So right now you have one people in the network, or you have thousands of people in the network. The change of the next phase of your KPI is determined by the current level of your performance in the network, which is represented by the alpha times KPI in here, the current KPI. And given what? And be given a certain very little amount of resource change. Because let's say now I have 7 people. I want to add another people, the 8th people. How the 8th people consume the network resource? I assume the new people will consume beta resource in this network. Okay, so this is the qualitative description of the relationship between the KPI and the network resource. Then you do the transformation. You are able to find the KPI is representing a minus exponential smoothing relation to the network resource. It's exactly matching such a smoothing relationship we call it a negative sigmoid curve in this term. Okay. However, we first, it's a qualitative description. Then we apply the mathematical formulas to prove it. The next step is we are going to use data to validate what we propose in here. And this figure actually is the validation results. Basically, you find, because we have many resources, dimensions, in each y-axis in one of these 4 figures. All the y-axis represents the cause-success rate. You are able to see most of the relation presents such a sigmoid relationship. But coming back a little bit, before I go to here, I want to exactly explain what this model is, because I'm here, let's use another figure to explain such a relationship. Just now, we have a conclusion that the relation presents like this way, right? A negative sigmoid curve between the cause success rate and one given network resource. However, in any network, we don't have one resource only. However, we have many resources, just like in the computer science. In the computer, you have memory, you have a CPU, you have hard drive, you have many kinds of network PC resources. Similarly, in wireless networks, you also have multiple dimensions in terms of these network resource. So what we are going to do is we expand a 2-dimensional space into the multiple dimensions space, meaning we have many resources like resource 1, 2, 3, blah, 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 like this. Based on our domain knowledge from a wireless engineer, we are able to prepare a short list of these network resources to be considered to model this given KPI, which is the cause success rate. Then what we are going to do is we expand such a sigmoid relation from 2D dimension, 2D space into multiple spaces. For example, like this way, right? In each space or in each 2D space, you are able to plot or you are able to derive such a relation based on our formulas just now. You agree in here? So far, so good? Okay. As per the first 2D space, we are able to identify, okay, that point is a cliff jumping spot. In that particular point, I find my network is crashed. However, after we expand the 2D space into the multiple spaces, right, we are able to identify the multiple cliff jumping spots in each dimension. You agree in here, right? Because after we expand the 2D dimension space into the multiple dimensions spaces, we are able to plot such a surface in each dimensions, right? The gray surface is organized by those blue curves in each dimension. So, by now, we are able to identify the cliff jumping spots in each space, and or I call it in each 2D space. Then we are able to make a projection. We project such all the jumping spots into our x-axis. I call it x1, x2, x3, blah, blah, all the x-axis represented by those network resources. After the projection, what we are going to derive is a green zone, or you call it a comfortable zone. Meaning what? Meaning as soon as your measured value stays in the scope of this green zone, you are able to claim your network performance is acceptable, right? Because it's safe for you to inside this green zone after your projection, right? So for each hour, each minute, the orange zone can denote, okay, the measured data set you measure every minute or every day or every hour. As soon as your orange zone stays in the scope of this green zone, you are able to claim your network performance is good, is acceptable. Okay. So this is the general idea that we expand our 2D space model to the multiple dimensions. And here, this is the validation results. In each figure, the y-axis denotes the call retention rate. Those different x1 and x2 axis denotes the network resources. Okay, then we are able to find the curve relation, the relation of the curve in here. Here it is very last case study, but this is very interesting. This case study related to your smartphone. So you will find that it may be more interesting to you. Device performance. Okay, so I remember 3 years ago when iPhone 4 is the first time commercial launched to our market. Do you remember at that time the quality, the radio quality? If you hold this, your iPhone 4, your call is always dropped. You remember? You cannot. You will find your bar disappearing immediately. I think most of the people remember this bug by Apple. Okay, we call it it's a low radio performance in the iPhone 4. So now there is a business requirement from our mobile wireless operators. Okay, we want to investigate if any new smartphone presents a poor radio quality or not. Okay, so this model is for us to identify if a cell phone or a given new smartphone presents a very good performance quality or not. I have 3 very small cases in here. This is case 1. I don't want to close which vendor is it, but this is okay, smartphone. Inside the smartphone, you are also able to find, okay, the customers start to complain. They hear the echo when they perform the voice calls. Then we come back to investigate what the problems are there. We almost check all the points, all the KPIs for this given device. But at very last, the thing very disappointing us is we find, okay, there's a ridiculous mistake. The microphone holder is missing when they manufacture this device. So this microphone holder missing caused very low radio performance, caused very high call drops, and caused very high hearing echoes in here. Case 2 is like this. A lot of customers is complaining, okay, they are suffering from the high call drop rate in some area. Then at last, we almost went through all the testing steps, and then we at last find the root cause is the screw pressure is defective. Then we come back to them asking them to fix this problem. Different kinds of the problems. This is the most ridiculous problem I have ever seen. It's similar to that iPhone problem. If you use your headphone or Bluetooth headphone to make any calls, the voice quality is very good, no call drops at all. However, if you use either your right hand or left hand, you hold the phone to make calls, your call starts to drop. It's similar to that iPhone issue. When you hold this phone, your radio linkage to the network may be lost immediately. This is also a net device performance problem we want to investigate. Okay, so after we studied all these different kinds of problems, what we want to do is we want to develop a dichotomous, a binary classification model to classify either a device based on their performance data to be a good sample or poor sample. So basically the 2 major points is we want to pinpoint which device in terms of probability presents the antenna performance problem or not. Then we classify a device into either an antenna pool cluster or into an antenna good cluster. So the last model for us to investigate the device quality is to do a classification model to classify either a new device is good or not in terms of their antenna performance. So this is how our classifier will work. Since we know because we have some very we have many problem devices and we have many good devices. It's like since we are going to do a classification, it's a supervised learning because for each device we have labeled them as either a poor device or good device in terms of their antenna quality. So in this case, we are going to do a classification in the model. How the classification will work is like this. We have the training data from the good antenna group and the poor antenna group. Then we leverage an algorithm in here to study their nuance in terms of linear or nonlinear formulas. Then we generate a classifier. Right? In here, we finish the training processes. Then in the future, once we have any given new data coming to us, we feed the new device data into this classifier, then to determine if this new device is good or not. This is, okay, please.
How many predictors did you use here?
Predictor, independent variables. I will answer you exactly in the next 2 slides, okay? You are asking a very good question. This is the first half of this model in terms of feature selection, right? But anyway, before I answer your question, let me finish this slide. Inside the classifier, what is this black box? Okay, we get the raw data from the good devices, from the bad devices. Then we divide the data into the training sample and the testing sample. Okay, we pick up 90% of the samples. Why pick up 90% of the samples is we want to do the k-fold validation in the very last step. So the k-fold, 10-fold in here counts 10% for testing and 90% for training. Okay, so we use 90% of our overall data as a training set. Then we go through your problem, okay, your question. We develop a formula in terms of feature selection to determine the best KPIs for us to do the classification. Once we finish the feature selection step, we are able to derive what KPIs are the best independent variables for us to do the classification. Then we feed the KPI metrics we select into this classification algorithm here to determine if the device is good or not. Okay, then I come back to you. Feature selection, which answers your question. 2 primary questions in here. What KPIs should we select? Then after we select the good KPI, proper KPIs for the classification model, what method should we do? Should we select or should we develop for the classification? First, to select the best KPIs, we have this solution. We call it feature selection. Basically, if you have studied let's say, the multivariate courses by Professor Sakamoto, you may have known some of the very typical formulas and methods for you to select best features for any model. For example, you can leverage Spearman correlation formula to test the linear relation between any input and output variable in here. Most state-of-art formula, we call it, or method, we call it information gain. We compute how much information per KPI contribute to this classification result. This is another method you may want to leverage here. However, in here, we develop our own method. I will introduce it in the next step. Then after we select the best features for the classification model, then we start classification. Right? This is, okay, we want to compute the similarity between any new device and the good group or the poor group. If the new device is closer to the good group, we claim this new device belongs to the good group. Otherwise, it presents the poor behavior and belongs to the poor group. Here, it's exactly answering your question. We developed a new method called spatial silhouette distance. We have a silhouette distance to determine the Euclidean distance between any two features. And in our case, since we have many features, many KPIs, we expand this formula from 2D dimension into the multiple dimensions. For each KPI, it's like a for loop. For each KPI, I compute the silhouette distance between any given feature candidate, KPI candidate. For its silhouette, KPI's silhouette distance between group A and group B. If KPI 1 helps a lot to separate good group from bad group, I would claim this is a good KPI in the classification. This KPI should be considered in the classification, right? Otherwise, if this KPI, let's say the values of the measured KPI in good group and the bad group are overlapped, almost completely overlapped, that means this KPI cannot effectively distinguish the good group from the bad group. So in this case, we claim this is a very bad KPI. We want to discard it in the feature selection process. Okay, this is a spatial silhouette distance model we newly developed. Then after we actually select the best KPIs, and then we have a new device coming to us. We want to determine if this new device belongs to the good group or not group. In here, we develop another group we call it. This is inspired by the k-means clustering algorithm. We apply the centroid distance formula to compute a new device distance in terms of those multiple dimensions of KPIs. If this new device is closer to good group or bad group, okay, this is, we compute the distance in terms of centroid distance. So this is assumption for the good group and the bad group. Matrix 1 denotes we have multiple dimensions of KPIs. Okay, then we have so many measurement points for each KPI. Matrix A denotes the good antenna cluster, the measured value of this good cluster. Then matrix 2 denotes the poor cluster. This is the new device cluster for us to validate. Okay. Then what we do is this. The green points and the green zone denotes the good performance cluster here because we have their measured value already. Then these red points denotes the poor performance cluster. We start from scratch. It's like this. Okay, we randomly pick up a point I in the good cluster. Then we calculate its Euclidean distance to all the other points in this green zone in its own cluster. So in this case, I'm able to derive its intra-cluster Euclidean distance for that particular point I select, right? So this very first step is to calculate the mean intra-cluster Euclidean distance for a particular point in that green zone here. Then you go to step 2. What you are able to do is you move forward to another point, I plus 1, to calculate its own intra-cluster distance. Then you do it for I plus 2, and here you finish all the points in the green zone here. This step is to calculate the mean intra-cluster Euclidean distance for a cluster you select. In our case, it's this cluster. We claim it as a good antenna performance cluster, just a good cluster, okay? By now, we finished the intra-Euclidean distance for the good cluster here. Then the next step is we want to compute the intercluster Euclidean distance for the same point just now. After we finish the intra-cluster distance calculation, we want to calculate how far it is from the bad cluster here. We still pick up the same point in here. We compute its Euclidean distance to all the points belong to the poor cluster here. Here is the intercluster Euclidean distance for any random point you select. Then we expand one point to multiple points. We move forward to next few points to see its intercluster Euclidean distance for the same cluster here. Then at last, we come to the spatial silhouette distance. Spatial silhouette distance is represented by the intercluster Euclidean distance between cluster good and cluster bad minus intra-Euclidean distance between cluster good and cluster bad, divided by the max of these two. What does that mean? It means if their inter-Euclidean distance is large enough, that means the KPIs we select can best separate the two clusters. If the intra-Euclidean distance is very large, that means the homogeneity of these two clusters are very close to each other. That means this KPI is not a good KPI to separate these two clusters. So overall, for this formula, we want what? We want the inter-Euclidean distance as large as possible. We want the intra-Euclidean distance as little as possible here. So the range of the spatial silhouette distance is between -1 and +1. So if the SD is close to 1, we are able to claim this KPI is a very significant feature for us in the classification. In the reverse direction, if it's close to -1, this KPI should be absolutely discarded because it contributes nothing, even it's a negative contribution in our classification. So this algorithm helps us to select the best KPIs for us to do the classification. Then the next step is after we separate the good cluster from the bad cluster, then we have a new device coming to us. What are we going to do? Okay, we want to know if this new device is similar to the good cluster or bad cluster. So we calculate what? We calculate the centroid. We calculate the centroid per KPI. For example, for KPI 1 in here, we call it the call retention rate. KPI 2 here is ISSI, which is another KPI we select. We have many KPIs selected based on the result of feature selection. So in here, I display a 2D dimension here. So after this step, we are able to identify the centroid for good cluster and the bad cluster. Then next step is I have a new device, right? I have a new device coming to me. The new device is the measured data of the new device is represented by this blue curve, with the blue area here. Then I'm able to identify the centroid for my new device. Okay, after I identify these 3 different centroids, I'm able to calculate the distance between my new device and the good group and between my new device and the poor group. I choose the one closer to the new device as the label of the new device. In this case, it's closer to green zone, so we can claim the device is acceptable in terms of the antenna quality. So this is the overall of the model for us to identify first, to identify the feature selection process. We select the best KPIs as the into the KPI metrics for classification. Then once we have any new device coming to us, we are able to leverage this formula to compute its centroid distance to either group. Then we make a conclusion which group it belongs to. The very last point in this presentation is in here. What if outliers? For example, these three centroids are the centroids we calculated just now in that slide, in the previous slide. However, if my new device has several outliers, right? Because we make a conclusion, the new device coming to us belongs to that green group because its centroid distance is closer, its centroid closer to the centroid belong to the good group, right? But if we have such a few outliers in this blue group for this new device, the centroid of that blue star will move to here. So in this case, an error is generated because the distance to the red star is closer. So in here, the result is overturned, right? Because the significant negative impact from the outliers in your new device measurement data. What we are going to do is we will replace the centroid with medoids, which is median points. Median points. In median points, it's not simply calculating the mean value. However, it is derived by the median value. So this centroid or this medoid is going to be moving back to the original place. So in this case, even we have so many outliers with medoids rather than centroids method, we are able to correct this mistake back to the original result we derive. So this is the strategy we fix the outlier problems. Basically, these are the three models for today. If you have any questions, please let me know. Oh, okay. So as I said, this is a supervised learning rather than unsupervised learning. Okay, in a supervised learning, you know the label of your device, meaning you know, okay, this device is a good or not. So I have thousands of devices coming to me. From the testing people, they make a label for me. After their testing, because they generate the measured data in the testing of this cell phone, right? Then they find, okay, this is really, for example, this is returned by you back to Verizon Wireless or back to AT&T. We know this is a problem device. We label this as a problem device already. We know this is, I prefer to trust in you, unless you are cheating me. You just want to return this device and you tell me a false reason, right? But of course, we have another step before we label it. We really test the performance of this device so that I get the measured data of this device. So I know this is a good or not. So in our classification, in all the training data, I know the label of each device already. So I can label this device is belong to in that green zone or red zone just now. This is a supervised learning. So thank you.